In our section today, we're going to continue in our unit on sequences and series, and we're going to talk about what a series is today and some special notation that comes along with it that's called sigma notation. Before we get into talking about what a series is, let's look back at an example from yesterday. So I've written this one out, so you're welcome to just follow along, or you can add in. I've given you the sequence 8, 18, 28, and 38. I want you to write an explicit and a recursive formula for this sequence. If you want to see how yesterday went, I would encourage you to pause the video now, try this example out to figure out your recursive and your explicit formula, and then you can unpause and see if you got the right solution. So let's go through this. For the recursive formula, remember the recursive formula goes with the previous term. So really, we just need to first start by figuring out the pattern. What's happening? Well, to go from 8 to 18, you want to think about, did we multiply or did we add something? I can't necessarily think of something that we multiplied by, but I can see that we added 10 to get from 8 to 18. We added 10 to get to 28, same to get to 38. So my guess is we would keep going by adding 10. That's the pattern. So for the recursive formula, to find the next term, which we call an, I need to know what the term is before it, an minus 1, and then I need to add 10. Then we need to tell it where to start, and so then we need to tell the formula, or the recursive formula, that the first term was 8. So then, for the first term, I would add 10 to get to 18, then I'd take 18, add 10 to get to 28, so on and so forth. So here, this is our recursive formula. Next up, we're going to do the explicit formula. Remember, for the explicit formula, we want to be able to directly plug in any value of n and it will spit out the number 18, or it will directly spit out the number 38. So here's a couple of things to think about here. For the nth term, what is happening each time? Well, every time I'm taking 8 and I'm adding 10. And if I think about getting from 8 skipping and going to 28, well, then I would add 20. Well, that's 10 times 2. So then if I think about trying to put an n on the 10, then when n is 1, that would be 8 plus 10. And so that would give me that value of 18. If n is equal to 2, I plug that in, that gives me 28, which is what we're looking for here. If n was 3, this would give me 38. Well, that's awesome. That gives us some of the numbers we're looking for. But the issue is that if I start at n being 1, which is where we usually start with the first term, that gives me 18 versus 8. So then what I need to do is I need to make it so that I could get a value of 0 here. So I'm going to change this to n minus 1. What happens then is when n is 1, the first term, that would give us 0 inside of here times 10 plus 8, which gives us a1 equal to 8, which is what we want. So it looks like this works here. If I wanted to see if this will give me 48 for the next term, I let n equal, we're on the 5th term, so I let n equal 5. That would be 8 plus 10 times 5 minus 1 is 4, which does in fact give us 48. So here's a quick reminder. So this is a recursive and explicit formula for a sequence. Today we're going to talk about a series. So let's go down to our notes. For a series is what happens if we take all of the terms of a sequence and we sum them up. So a series is the sum of all terms of a sequence. We're going to take our list and we're just going to put a plus sign between them and add them up. Going down to our second bullet point, the nth partial sum, is the sum of the first n terms and is written as a capital S with a subscript n, S sub n. So if I wanted to take a sequence and add up the first 5 terms, that's called the 5th partial sum, and then my Sn would read S sub 5. Just like we saw yesterday, a series can be finite, it can have an ending, or it can be infinite. series means it's the sum of a sequence. So we're taking a list of numbers, we're adding them together, and usually there's a pattern. So with a sequence, I can write that as a specific explicit formula. So in order to talk about the sum, we can use that formula in a notation called the sigma notation. Right here, this symbol is called a sigma, and it stands for the sum of a list of numbers. So we would add the numbers with plus signs in between. When we have the sigma notation, we start and we put the sum, the sigma, at the beginning, and then we put our explicit formula, or sometimes we'll also put a recursive formula to the right of it, meaning we're going to sum up each term in the formula. Then, underneath, we give it a starting value, and this could be, let's say we started at 1. This starting number here, the first number, would be substituted and written below the sigma. The final number that we want to stop with is what goes at the top. Let's say I wanted to sum up the first term to the 100th term. Then we would put n equals 1, or you can use k, any letter we want, all the way up to 100. So a good example here is shown in our last bullet point. This is what it might look like to write something in sigma notation. It's the sum of where from n equals 1, and the starting value doesn't have to be 1, all the way up to some final number k. And now they're showing each of the terms of a sequence being added up. So let's look at a couple of examples of what it would look like to find a sum or to find a partial sum. For this first sum, they ask us to find the fifth partial sum of an equals n squared minus 3. This is an explicit formula for a sequence, and we want to find the sum of the first 5 terms. So in order to do that, we need to actually find those terms. So we're going to use our explicit formula. We'll start at a1. So for a1, this would be 1 squared minus 3. So that would give us negative 2. For a2, that's 2 squared minus 3, which is 4 minus 3, which is positive 1. Next up, we have the third term, which is n equals 3, 3 squared minus 3. That gives us 9 minus 3, which is 6. Next up, we have the fourth term, 4 squared minus 3. Hopefully we're catching the pattern. That's 16 minus 3, which is 13. And then lastly, fifth term, 5 squared minus 3. That's 25 minus 3, which is 22. So for the fifth partial sum, we would denote this as S sub 5. That means it's the sum of the first 5 terms. And now that we know them, we'll just add them up. That would be negative 2 plus 1 plus 6 plus 13 plus 22. Now all we need to do is add them up. So negative 2 plus 1 plus 6 plus 33 plus 22 gives us a sum of 60. So the fifth partial sum of this sequence is 60. So this is one way it can be shown. They'll give us the fifth partial sum. They could also give it to us in sigma notation as shown in example 2. They ask us to evaluate from n equals 1 up to 4. That is from the first term to the fourth term using this explicit formula n squared minus 2. So just like we did the first time, we need to figure out these values. So for the first term, a1, that's 1 squared minus 1. That gives me 1 minus 1, which is 0. For the second term, that's 2 squared minus 2, which gives us 4 minus 2, which is 2. The next term, a3, is 3 squared minus 3, which gives us an answer of 6, 9 minus 3. And then lastly, the fourth term, which is 4 squared minus 4, which gives us 16 minus 4, which gives us 12. So now, this is S sub 4, or you could also go back to our sigma notation. Either way will work here. The fourth partial sum is 0 plus 2 plus 6 plus 12. That gives us 8 plus 12, which gives us a partial sum of 20. So hopefully you can hear the vocabulary that I'm using. When we're adding up a couple of terms, it's a partial sum of an entire sequence. We're taking one section and adding up those terms. Let's go and look instead. What if I give you a series? We can tell it's a series because rather than commas, there's pluses. And we want to condense this and write it into sigma notation. There's a couple of different pieces that we need. The first piece is our structure. This can condense down to the sum, so the sigma of something, from some starting number n all the way up to some number at the top. So we're going to fill in values here. And then there's some formula that we'll put here, and it will be an explicit formula that captures the pattern we see happening with each individual term. So now it's time to go back. As I look over to each of these terms, what I want you to think about is, do you notice patterns? The first thing I notice is that every single term in the sequence has the same number on top. That's a 5. So in my explicit sequence, the 5 doesn't change every time. So we can just put a 5 on top. That means every term will have a 5 on top. The bottom, I also notice that the first part of the denominator has a 1. So it's 1 plus something. Now the number that's changing each time is that second number. We go 1, 2, 3, and so on and so forth. So that is the point where the number that's changing, that's where the n comes into play. 5 over 1 plus n. Let's try it out. Third term, n is 3. For the third term, that's 5 over 1 plus 3. That matches with what I see in the third spot in this series. So then we need to fill in our bounds. What is the first value of n that we would need to plug in to get a 1 in that spot? Well, that would just be n is equal to 1. So we're going to start from n is equal to 1. And then where do we stop? If I started at 1, well then what would I need to plug in to get a 15 on top? That would be a 15. So we would go all the way from n is equal to 1, all the way up to the 15th term. And this is the sigma notation version of that expanded series that they gave us here. All right, let's look at another example. Okay, example number 4. Again, I have a series, and I want to write this in sigma notation. So I know that I have the sum, and just to show you, I could use any number. You could use n, you could use k. I'm going to use a k this time because it just needs to represent a variable. So as I look, there's a couple of things that I notice. Each time I have a fraction. How are these fractions going up? It looks like to get from each fraction, we are multiplying by 1/2 every time. To get from 1/2 to 1/4, we're also multiplying by 1/2. And so in this case, I need to figure out some way to get this number every time. To get to 2, that's 2 to the first power. To get to 4, that's 2 squared. To get to 8, that's 2 to the third power. 128, you might not be familiar, it is a power of 2, and we'll get there in a second. So it looks like the number that's changing is there is 2, and then it's being raised to exponents that are going up by 1 each time. So what that can give us here is the 1 on top stays every time, and then this is going to be 2 to the n power. Awesome. So we figure out this is 1 over 2 to the n power. So if I let n equal, actually we used k, sorry, let's go back, let's make this 2 to the k power so that it matches. So as long as whatever letter you put has to match what you put in your formula. All right, so this time I'm using k. Let's say that k is 1. That would give me 1/2. Awesome, that gives me my second term. 3 would give me 1/8. That's this term right here, and equals 2 gives us 1/4. So it works, the pattern is working, but how do I get this first term? What I want you to remember is this is the same as having it written as 1 over 1. Now we ask ourselves, what exponent of k would make 2 to what power gives us the answer of 1? Think about it, and hopefully you can figure out that answer is 0. So I would have to start at 0 in order to get a value that gives us 1 as a starting. So 1 over 2 to the 0 power gives me 1. And then lastly, what would I have to plug in to get 128? You could try this out. So we're asking 2 to what power gives me 128. If you try this out, just multiplying by 2, we're going to have to multiply 2 7 times to get 128. So our upper bound would be 7. So now we have it. We have an explicit formula, a starting value, and an upper bound. This is our formula. Now, there's a couple of pieces that the structure will stay the same, but we can modify a couple of numbers. I'm going to show you this as an example scenario. This series, written in sigma notation, is not the only way I could have written this. Let's say instead we made another decision first. The order that we pick the starting number or explicit formula, those can sort of change. Let's say that a lot of times mathematicians like to start at 1. You don't have to. We started at 0 and it works, but a lot of times mathematicians like to start at 1. So if I start out, I know I have 1/2 to the k power. If I make the decision that I am starting at 1, then if I just make this 1/2 to the k power, then that's going to give me 1/2 as the starting term. That's not going to work. So instead of adjusting the number k equals 1, we'll adjust the exponent. So how do I get a number, plug in 1, and make it equal 0? I just need to add a -1 in the exponent. So 1/2 to the k minus 1 power. That shifts everything back by 1. So if I plug in 1, that gives me an exponent of 0. If I plug in 2, that gives me an exponent of 1, and so on and so forth. So then lastly, for my upper bound, rather than plugging in 7, in order to get the exponent I want, I would need to go up to 8. So this is the exact same series, just written with a slight modification. So you'll see this in the answer key. You'll see a couple of examples that all mean the same thing with some shifts. So these are the biggest examples we've seen so far with series. If you feel comfortable at this point and want to give it a try, head on over to the practice. I am going to go through one more example. So if you want to watch one more, stick here and then head to the practice from there. Here's the last example. So this time, there's a couple of things I noticed. As I try to figure out a pattern, I don't figure out any multiplier that gets me to the next, obviously, but I do see that I'm starting with all the numerators are going up by 1, and all the denominators are also going up by 1. So as I start with my sigma notation, and I start with my formula, as I can think about these index, plugging in the numbers 1, 2, 3, 4, well, it looks like if I plug in n on the top, then I could, as it goes up by 1, the numerator of each term will go up by 1. And then the same works on the bottom. I just need to start 1 bigger, so I could make the top, or the denominator, n plus 1. Let's try that out real quick. If I plugged in n is equal to 1, that would give me 1 on top. 1 plus 1 is 2. That works. Let's try 2. It gives me 2/3. That works. So then where do we need to start? We would start at n equals 1 because I want to get 1/2 out of this. Now where do we end? New from what we've seen before, they don't give us an end value. They just give us a ... That means that what we have here is an infinite series. And so it goes on forever. Since it's an infinite series, we're going to keep expanding this pattern out to infinity. So that means for our sigma notation, rather than writing a specific number, we'll write infinity to represent that it goes on indefinitely. And this is our sigma notation. This is our sigma notation for the given expanded series. And that is the end of this lesson. If you need more practice, I will link a couple of extra videos in Schoology from some other people on YouTube that might help you along with this as well. That is the end of our section.